Hello, guys, and welcome to Critical Concept. So, today we are going to start a new series to learn CFD, computational fluid dynamics, industry level computational fluid dynamics, of course, not college level. So, the motto of this series is to make you independent in CFD, and it is something like a virtual internship for you. So, when you are going to apply any organization, any company, okay, so you have to learn CFD from somewhere else, and at that time you can apply. So this is just for bridging the gap between the college to pass out student and the industry. So when you are from college pass out, and after that you are joining a industry, there is a gap, so you have to bridge that gap, and this course will help you to bridge that gap. So let's begin with the CFD boundary condition first. Okay, so majorly objective is that you will understand how the industry work in CFD, all that things I will come there, but before that let's understand the boundary condition. That's the most important critical part of the CFD, and after that we will go for meshing, and after that we will go for all other points like physics definition for various cases. One by one we will explore each and every cases. Okay, and so let's start with the boundary condition, because boundary condition, what does it signify? Okay, so because that is the most important point, because that is something through which you talk to the code, actually backend code, the tool. You says that tool, hey, you do this for me, that for me. So code understand through your boundary condition definition. Okay, so let's try to understand what is CFD boundary condition. CFD boundary condition is at first we will start with the stagnation inlet. Stagnation inlet is nothing but the stagnation pressure is nothing but as we know, static pressure plus dynamic pressure. So let's understand it in little detail. Okay, static pressure and dynamic pressure. So what is stagnation pressure? Let's understand. Suppose the water is flowing from 0, 1, 2, 3. Okay, so 0 is the entry, 3 is the exit environment, and through this pipe, and the water is flowing in the downstream. So what is static pressure and what is dynamic pressure? Okay, so static pressure is nothing but the from 0 to 3, whatever is the system resistance. System resistance means friction resistance or any other resistance, like major resistance, minor resistance, whatever we have read, gone through the sudden expansion, sudden contraction, all kind of resistance it considers. Okay, so 0 to 3, whatever is the resistance, that is nothing but the static pressure at 0, because environment it is gauge pressure 0. So definitely in the 0, the static pressure is that resistance, and dynamic pressure is nothing but the corresponding the counterpart of the static pressure, and it is nothing but the defining the velocity, through which velocity it is going through the you know pipe, actually. Okay, suppose let's take a pump here. Maybe if we take a pump here, this is a pump, or let me make it bigger. Okay, and there is a pump, and the water is flowing from pump to entry. Okay, maybe. Okay, so at that time, how the things are occurring. So when we are running the pump in a higher RPM, a higher power, high power pump, at that time what we will get? We will get more thrust. Okay, more flow, right. But after certain time, flow rate will change as well as pressure will change. So there we will get more thrust as well as more flow. That means we will get both the increased more pressure and more flow. So all that things about the pump characteristics, all that things I will discuss later. But for the simple case, let's try to understand what is static pressure and dynamic pressure first. So static pressure is nothing but the system resistance, and dynamic pressure, because environmental pressure is 0. So in actuality, if it is the environmental pressure is something, so in that case static pressure is the system resistance plus environmental pressure. Okay, so and dynamic pressure is nothing but the kinetic pressure, whatever is the kinetic energy. Okay, now Through the system, dynamic pressure remains constant and static pressure reduces like this, because static pressure is to overcome the system resistance. Okay. And next is that, now when you are applying the stagnation inlet boundary condition, the code understands, suppose at point 0 you are defining stagnation inlet maybe 100 pascal. Okay. So code understand from 0 to 3 what is the pressure reduction, what due to overcoming the frictional losses, sudden expansion, sudden contraction, and all that losses. Code understand that, and the code evaluate the uh, sorry for I received one call. I just got the call. Okay. And code evaluate the back pressure accordingly. So based on the restriction, system resistance, so the downstream resistance, code calculate the back pressure, that is called static pressure. And dynamic pressure is the through which velocity water is flowing through it. Okay. Because water is incompressible here and with a constant velocity. And that's why when water is incompressible and mass flow of the water is constant, the velocity should be constant. That is the reason. So dynamic pressure is remaining constant, and water static pressure, it is remaining dependent on the downstream resistance. Okay. And after that, once the total pressure is defined, the code auto calculates the total pressure from static pressure from the system resistance, and it subtracts the total pressure minus system resistance. It subtracts the total pressure sorry static pressure or system resistance from the total pressure, and it gets the dynamic pressure, and accordingly it calculates what is the mass flow is traveling through this. Okay. That is the way the stagnation inlet is defined. Next step is the velocity inlet. You are only defining the dynamic pressure at point 0, and the system resistance just opposite. So code get the system resistance from the geometry and downstream geometry, and from there it calculates the system resistance, and the system resistance addition with the dynamic pressure, whatever you are defining velocity inlet, it is nothing but the total pressure. And after that, next is the mass flow inlet. Mass flow inlet is something similar to the velocity inlet. You are defining the mass flow, it is traveling through this, and from there the code is getting the mass flow velocity. But mass flow inlet little bit different with the velocity inlet. When the flow is compressible, that also depends on the geometrical shape and the size and diameter of the pipe. But yeah, but for simple case, let's start with the incompressible mass flow inlet. When you are defining the velocity, nothing but the velocity. And when you are defining the velocity, at that time you are uh, uh, defining the dynamic pressure, and the static pressure is nothing but the system resistance. Okay. And system resistance, so total pressure at point 0, code will automatically evaluate. And outlet is the condition, is the what is the sometimes what we do in the outlet boundary condition. It is the just outlet boundary condition, and here we provide the outlet. And what is the mass flow rate? So code understand, suppose something is open to environment, and some suction process is going on. Okay. And you know that suction outlet is means suction is occurring through outlet, means through outlet. And the mass flow rate and corresponding the pressure data will be in the suction zone, that will be evaluated through the you know uh, evaluated through the back pressure. Actually, back pressure, what I'm saying, suppose some suction is occurring in the outlet, this will assume, just try to understand this is a very interesting concept. So at point 3, suppose the it is outlet. Okay. So and at this point it will consider stagnation inlet 0 pascal. Okay. So stagnation inlet 0 pascal, when you are giving it to the environment, and it is sucking, and outlet maybe 5 kg, or maybe zero point 0.5 kg per second. Okay. 0.2 kg per second maybe. And outlet and inlet boundary condition is the stagnation inlet. So at that time code will understand, so stagnation pressure is zero, so static pressure will be negative, and dynamic pressure, because there is some suction, dynamic pressure will be there positive. Okay, so that's why the static pressure will be negative but dynamic pressure will be positive. Okay, and due to the having that strong dynamic pressure, the code will understand that, hey, this is nothing but this is outlet boundary condition, but strong dynamic pressure will suck the flow, and static pressure will be negative but strong dynamic pressure will suck the flow, and it will go through this is called the outlet boundary condition. And also another outlet boundary condition is the pressure outlet boundary condition. Pressure outlet is very simple boundary condition. When you are defining the pressure outlet, you are defining the pressure data at this point. Suppose your static pressure data at this point, static pressure data, and after that, pressure, after that you also apply the suppose stagnation inlet here, and here static pressure. So code get a very good idea that what is the system resistance, and from there it evaluate means when you have the stagnation pressure at the inlet and when you have the static pressure at the outlet. Okay, and you have the system resistance. Okay, so the static pressure at the inlet also, because static pressure at the outlet, it suppose 5 pascal, and system resistance at the inlet, system resistance in the entire system, it is maybe 2 pascal. So the static pressure at the inlet is 5 plus 2 7, and if code gets that 5 plus 2 7, and after that code evaluate, and whatever you are defining stagnation inlet, so code will evaluate that 7 pascal, and suppose you are defining 10 pascal stagnation inlet, so 10 minus 7, that is nothing but the dynamic pressure, that is nothing but the dynamic pressure that is important for the velocity of the flow, and from that could evaluate the flow velocity. Okay, so this is the basic of CFD. In this series you will get the learning from the CFD from the industry experts. I have an experience of 8 years in a multinational company, and so this kind of expertise you get it only through the working in industry, not in college. So this course is to bridge the gap between the college and the industry. Okay, so when you will attend this course, you will get the actual understanding of the CFD and actual practical application of the CFD, and that's the most important part of the CFD. So guys, if you have liked the video, please share with others and subscribe the channel, and definitely this will be helpful for you over the long time. And please do like, share, and subscribe. Definitely we'll learn the CFD step by step from zero to hero, and we'll learn from the basic pipe flow to any kind of complex CFD. Okay, so the industry level CFD we'll learn one by one, step by step. Maybe in next 6 months or 1 year we'll learn it. And please do subscribe the channel, and thank you very much. Thank you very much. Have a great day.